Imagine a world where your health is, well, constantly monitored. Not in a hospital, but just as you're living your life. What if tech could give us a real shortcut to, staying informed about our own health anytime, anywhere?
Yeah, it's a compelling idea.
So today, we're diving deep into exactly that area. Wireless body area networks, WBANs for short. We're looking at a really cutting-edge paper just out last month, August 2025. It's from the International Journal of Advanced Research in Science, Communication, and Technology.
Right, the title is Three-Tier WBAN Communication, Design and Performance Evaluation by Sudik Das and the team.
And our mission here is to really unpack how these networks actually work. What are the big challenges? And maybe most importantly, how are new innovations making them better, more efficient, especially when it comes to saving energy?
Exactly. And by the end, you should have a really good sense of how this research gives us critical insights into where healthcare tech is headed. Pretty exciting stuff.
Definitely. So let's start with the why. Why do we even need these W bands? The paper really lays out this stark global healthcare challenge. It cites the U.S. Census Bureau.
Yeah, the numbers are pretty sobering. The world's older population predicted to basically double from about 375 million back in 1990 to, get this, 761 million by 2025. That's a huge shift.
The demographic tsunami, like you
Yeah.
said. And that rapid growth, plus fewer healthcare facilities in some areas, it creates this massive need for, well, proactive monitoring, right?
Yeah.
And affordable monitoring.
Absolutely. And the paper makes a crucial point. Many chronic diseases, if you catch them early, they can be managed, controlled. But sadly, thousands of lives are still lost just because diagnoses don't happen in time.
So the urgency is there.
Very real.
Okay, so enter W bands, wireless body area networks. These are positioned as the solution. We're talking about intelligent, tiny biomedical sensor nodes, BSNs. You can implant them or just wear them.
That's the core idea. And what's really game-changing is the freedom they offer. It's an economical system, potentially, for doctors and patients, but the huge advantage.
Mobility. Right. You as the patient could just go about your day. Work, exercise, whatever. You're not stuck in a hospital bed, not needing someone constantly watching over you in person.
That freedom is key. It shifts the whole paradigm of care.
Now, you mentioned they emerge from wireless sensor networks, WSNs. But the paper says WBANs have unique challenges. What makes them so different? Is it just because they're on a person?
Well, yeah, that's a huge part of it. The environment, the human body is fundamentally different. Unlike a sensor in a factory, these have to deal with constant movement, interference from body tissue itself, and critically, very limited power. These things have tiny batteries.
Okay, that makes sense. The human factor. So given those constraints, how does your body literally become a network? The paper talks about this three-tier system.
Right, it breaks down pretty logically. Tier 1, that's the intra-WBAN. It's the network right on or in your body.
Okay.
These small, low-power sensors, the BSNs, they're collecting vitals. Think heart rate, blood pressure, O2 saturation, temperature, that kind of thing.
And all the key stuff.
Yeah. And they send that data to something called a body node coordinator, or BNC.
And that BNC, maybe it's like a dedicated device or even just your smartphone, that takes us to Tier 2.
Exactly. Tier 2 is inter-WBAN. It bridges the gap between your body and, well, the outside world. The BNC collects the sensor data and shoots it off to a remote medical site for analysis. It might even do some basic filtering first.
Okay, so body to phone, phone to cloud, sort of.
Pretty much. And Tier 3 is that beyond WBAN layer, the remote part. This is where you have medical servers, cloud platforms. They process, analyze, store all that data.
And provide the actual services, like
Yeah.
real-time diagnoses, patient records, emergency alerts.
All of that. Alerts to doctors, caregivers, emergency services if needed. It closes the loop.
Wow. It's quite an ecosystem, all starting with these tiny sensors. And the communication relies on standard wireless protocols, right? Like Bluetooth, Zigbee.
Yeah, Bluetooth, Zigbee, and there's a specific standard too, IEEE2 802.15.6, designed for these kinds of body networks.
Okay. But now for the tricky part, the challenges. You mentioned power earlier.
Yeah.
The paper says data communication uses, what was it? Almost 80% of a sensor's energy.
80%, yeah. It's incredibly power hungry.
That sounds like the absolute killer problem, keeping these tiny things running.
It is. Short battery life is a massive hurdle. If a sensor dies, especially one tracking something critical, it could be genuinely life-threatening.
Okay, yeah.
So the core problem for researchers is designing for energy efficiency. Specifically, how do you choose the next node to send data through the next hop to make those batteries last as long as humanly possible?
Right. So
Yeah.
why not just have every sensor talk straight to the BNC, the phone or coordinator? Seems simpler.
Good question. It seems logical, but it comes back to those limitations. The sensors have short range, the signal gets weaker over distance, that's path loss, and sending directly just eats up too much power for long-term use.
Ah, okay. Like shouting across a room versus passing a note.
Exactly. It's just not sustainable for continuous monitoring.
So that's where multi-hop communication comes in, passing the data along, sensor to sensor, towards the BNC.
Right. Relay the data through neighboring nodes. It helps balance the energy load across the network.
But there's always a but.
Yeah. It creates a new critical challenge. How do you pick the best neighbor to forward the data? The best next hop node?
And the paper says current methods often just pick the physically closest one.
Many do, yeah. They go for the shortest path, but that's not always the highest quality path, especially in terms of energy. Picking the closest might actually drain a crucial node faster or lead to more transmission errors, ultimately costing more energy.
So shortest isn't always smartest here.
Definitely not. It's about the most efficient, most reliable route considering everything.
And then there's the human factor again, the body itself messing things up.
Oh, absolutely. Think about it. You move, you walk, run, even just wave your arm. Those sensors can shift. That changes the network layout, the topology. Links between sensors might break. Plus, our body tissue. It absorbs and scatters radio signals, like trying to talk through a pillow.
Wow. So the signal strength and quality can just tank because you, well, moved.
Precisely. It significantly impacts the signal. So the network has to be constantly adapting to this squishy, moving environment. It's a unique engineering puzzle.
Incredible complexity. Okay, so given all that, the power drain, the movement, the body interference, how are researchers making these networks tougher, more reliable? The paper proposes this ELRW framework.
Yes, ELRW, Energy-Aware Link-Efficient Routing Approach for WBANs. The goal is green communication, basically, making the links energy efficient and smart.
And what's the key innovation there? What makes it different?
What's really clever about ELRW is how it calculates the quality of a link. It doesn't just look at distance or remaining battery, which others do. It specifically factors in things like path loss.
Okay, how the signal bounces around and gets weaker.
Exactly, and interference effects. It builds a much richer picture of how good a potential path really is, moment to moment. It's designed for this dynamic on-body environment.
So it's like a super smart Waze for data packets on your body, considering energy, interference, signal loss.
That's a pretty good analogy, yeah. It involves modeling the network, calculating the cost of each potential path based on this energy-aware link efficiency, and then making the smart choice for the next hop.
And the results. The paper says it shows real benefits.
Yeah, the comparative evaluations showed significant improvements in energy efficiency for these kinds of medical body networks. It makes them more robust.
Okay, that's ELRW. But you mentioned there are other approaches too, right? Just to give context.
Definitely. It's a busy field. For example, there are thermal-aware protocols, things like Emittempty and an improved one called Reattempty.
Thermal aware, like temperature.
Exactly. They worry about sensors potentially overheating tissue if they transmit too much. So these protocols change routes based on temperature thresholds. Safety first.
Makes sense. You don't want the cure to be worse than the disease.
Right. Then you have protocols focused on quality of service, QoS, like QPRD. These prioritize getting the critical data through quickly, even if it costs a bit more energy, while maybe delaying less important data. It's a balancing act.
Okay, so prioritizing based on urgency.
And another interesting area is cooperative communication. Protocols like CoLE-EBA use nearby helper nodes to boost the signal or relay data if a direct link is weak. It improves reliability, reduces energy wasted on retrying failed transmissions.
Like getting a little help from your friends.
Sort of, yeah. And looking ahead, people are exploring AI and machine learning, things like particle swarm optimization, genetic algorithms, using these advanced techniques to make routing decisions even smarter and more adaptive.
Really cutting edge stuff. Okay, so bringing it back to this specific paper and their contribution, they introduced something called IMQRP.
Yes, the improved QoS-based routing protocol, they validated it using simulations.
And what were the tangible improvements they found with IMQRP?
Several key things. It apparently selects more feasible, more reliable routes. Critically, it showed significant improvement in network lifetime, keeping those sensors alive longer.
That's the big one.
Absolutely. And fascinatingly, it uniquely considers the patient's postural movements when figuring out where sensors and relay nodes should ideally be placed or how routes are chosen.
Whoa, okay. How does factoring in posture actually help?
Well, think about it. If the system knows or can predict typical movements sitting, standing, walking, it can anticipate how the links between sensors might change. It can proactively choose routes that are likely to remain stable despite that movement.
Ah, so it's building a network that's designed to flex with you.
Exactly. It leads to better overall quality of service. The simulation showed improved residual energy, batteries last longer, a higher signal-to-noise ratio, or SNR.
Meaning a clearer signal.
Right, less noise, better clarity, stronger link reliability, and ultimately a better received signal strength indicator, RSSI. Basically, the signal arriving at the coordinator and eventually the medical center is stronger and more reliable. More data gets through successfully.
And they compared this IMQRP against others, like that QPRD and co-LAAB you mentioned.
They did, and the simulations showed IMQRP performing better across these key metrics: residual energy, QoS, minimizing path loss, better SNR. Pretty convincing results from the simulation data.
Okay, so let's recap. We've gone deep into this world of wireless body area networks. We've seen why they're so vital for future healthcare, the tiered structure, the huge challenge of energy, the impact of just moving around.
And the really ingenious ways researchers are tackling these problems, like with energy-aware routing like ELRW, and specifically this IMQRP protocol focusing on QoS and even posture.
Looking ahead, the research suggests integrating these WBANs with smart homes using IoT tech, using relays placed strategically.
Yeah, the paper touches on that. Deploying efficient multi-hub setups, maybe placing relays, say, 50 to 75 centimeters away from sensors, could drastically cut path loss and save energy in a home monitoring scenario. These relays seem crucial for robust systems.
Right. But that leads to a really interesting final thought, doesn't it? These relays, while great for performance, the paper also mentions they add cost, more hardware, maybe more batteries to replace.
Exactly. It brings up a critical question for all of us as this tech develops. We have these amazing capabilities, potentially life-saving monitoring, but how do we balance that cutting-edge function with the real-world factors of cost and maintenance?
How do we make sure this vital technology is actually scalable, affordable, and practical for widespread long-term use? That seems like the next big hurdle beyond the purely technical ones.
It's definitely something we need to think about as these systems move closer to being part of our everyday lives, a crucial balancing act for the future of connected health.